In this video, we're going to be talking about Fourier transform infrared spectroscopy, also known as FTIR. So the basic idea of an FTIR spectrometer is that you have IR light and it passes into your sample. Some of that light gets absorbed by your sample, which we'll talk about in a second, and the remainder of the light is going to reach a detector, which is connected to a computer, which is going to then show us either the light that was transmitted or the light that made it through the sample, or the difference between the light that went into the sample and the light that went out, which is known as the absorbance spectrum, which is how I've shown it here. So how does your sample absorb infrared light? It turns out that your infrared light gets absorbed by vibrational motion or molecular motion. So it doesn't have to be stretching, it could also be bending. Here I've shown a stretching motion of water. So the red here is oxygen, the gray is hydrogen. So we can think about around 3600, we have stretching motions where those hydrogens are stretching away and then back towards the oxygen atom. And around 1250, we have another motion, or around 1600, we have another motion, which is the bending motion of water. So now we can think about those hydrogens are coming closer together or further apart, making the angle of the hydrogen-oxygen-hydrogen change. So it's bending back and forth. And so anytime our molecule has an available motion, many of those motions are going to be able to absorb infrared light, and this is going to excite those motions or make them happen more exaggerated, right? So they're always sort of happening, but this sort of kicks them up a notch, and so they're dancing a little bit more excitedly. Note that on our instrument, the absorbance should never be above 1.2 if you're thinking about absorbance mode. This is because that basically corresponds to no light reaching the detector, or so little light above 1.2 reaching the detector, so all of it is being absorbed by the sample, nothing's reaching the detector. So that means that your detector is sort of just collecting noise. So it can't distinguish between different amounts of noise. So if you care about a peak, you really should make sure that your absorbance is not far above 1.2. If you're simply looking at that the peak is present and not trying to analyze the absorbance of that peak, it's allowed to go above 1.2. If you're measuring in percent transmittance, like you do in organic chemistry, that would correspond to not reaching all the way to 0% transmittance. So your peak should never go all the way to 0%. The other thing you should note is in absorbance mode, your peak should never go negative or go below 0. In percent transmittance, they should never be above 100%. These are illogical values and probably mean that you've done something wrong and you should seek help from an instructor or a TA. So let's talk for a minute about attenuated total reflectance, or ATR FTIR, which is a very common way of collecting an FTIR spectrum. Here, we still start with IR light, but now our IR light doesn't go directly into our sample. It actually goes into this zinc selenide diamond crystal. And there are other types of crystals, but our instrument has a zinc selenide diamond blend. And our sample sits on top of the crystal. So when you put your sample on that silver plate that has what looks like a hole in the middle, that hole in the middle is that crystal. It's the top surface of that crystal. So your light goes into this crystal and reflects up into the bottom very interface of your sample. Just where your sample is barely touching the crystal, the light gets reflected up into your sample. Now, the sample has molecules in it, and so they can absorb IR light. And so some of that reflected light gets absorbed by your molecule, and every time that reflected light comes back down and touches the zinc selenide diamond crystal again, it interferes with its reflection. And so what comes out of the crystal is actually this interfered light or disturbed light, and so it's not quite what we've put in. And so we measure that with a detector, and this involves a little more on the computer's part. Here the computer actually has to translate this interfered light or this interfered pattern into an FTIR spectrum. And there's a lot of fairly complicated math and algorithms that go into that. Here I've shown it in percent transmittance, so coming down like you might see it in organic chemistry. So FTIR, as the name suggests, it has a Fourier transform. For those of you who've maybe taken some more advanced physics or mathematics courses, you have an idea that something a little more complicated is going on. So our IR light does not go directly into our sample or directly into the zinc selenide crystal. There's a few more complicated optics that go on in there, both on the front and on the back end. But we'll save that for another day. Hopefully this is enough to get you into FTIR and give you a brief idea of what's happening.